All right, welcome back, everyone. Today, we're going to level up our game when it comes to recursion. If you're already comfortable with a function calling itself once, you are totally ready for what's next. So let's just dive right in.
So here's the big question. What on earth happens when a function, inside its own logic, doesn't just call itself once, but twice? This, my friends, is where recursion gets incredibly powerful, and yeah, a little bit mind-bending. It's the secret to cracking a whole new class of problems.
So here's the fundamental difference, right? On the left, you've got your standard single call recursion. I want you to think of that like walking down a single straight path. But on the right, multiple call recursion, that's more like a path that's constantly forking, creating this branching tree that we have to explore.
And to really wrap our heads around this whole branching idea, there is no better example out there than a problem I bet many of you have seen before, the good old Fibonacci sequence. It is the absolute perfect case study for this.
Just as a quick refresher, the Fibonacci sequence is just a series of numbers where any number is the sum of the two that came right before it. So you start with 0 and 1. The next one is 0 plus 1, which is 1. Then 1 plus 1 is 2. 1 plus 2 is 3, and on it goes. It's a simple rule, but believe me, it has some huge implications for our code.
And boom, right there, that's the magic of it. The mathematical formula itself is recursive. To get the nth Fibonacci number, you need the one right before it, f of n minus 1, and you need the one 2 steps before it, f of n minus 2. You see it right there in the formula. It's practically screaming at us that 2 calls are needed.
Now, I know what you're thinking. Couldn't we just solve this with a simple for loop? And yeah, you absolutely could. In fact, it'd be way more efficient. But that's not the point today. We're using Fibonacci as a scalpel to dissect how these multiple recursive calls really work under the hood, because this pattern shows up everywhere in more complex algorithms.
Okay, so let's get our hands dirty. It's time to trace the execution path. We're going to pull back the curtain and watch the step-by-step journey the computer actually takes to get to that final number. This right here is the single most important question you can ask. When our code says f of n minus 1 plus f of n minus 2, do those two things happen in parallel? Does the computer multitask and work on both at once? And the answer is a big, resounding no. This is the absolute key takeaway. Code runs line by line, one after another. The first call, f n minus 1, has to go on its entire recursive adventure, do everything it needs to do, and return a final value before the program even looks at the second call, f n minus 2. It's a one-track mod.
Okay, so let's trace fib4. The function starts, it sees it needs fib3, and it immediately calls it. And then, it just waits. The entire fib3 branch has to go off and do its thing, eventually coming back with the answer, which is 2. Only then, once fib3 is completely done, does the fib4 function wake up and say, okay, now for my second call, fib2. That branch runs, comes back with 1, and finally, fib4 can add the two results together. 2 plus 1 equals 3.
I mean, trying to trace all that line by line, it can get super confusing, right? A much better way to picture what's happening is to turn that horizontal code into a vertical structure, the recursion tree. And here's the pro tip: the real mental leap is connecting what you see in the code, that horizontal line after line execution, to this vertical, branching tree. It's the mental model that brings order to the chaos. And here it is, the whole process as a tree. Up at the top, fib4. Its first call is to fib3, so we dive all the way down that left-hand side. Fib3 calls fib2, which then calls fib1 and fib0. Once that entire left branch is totally resolved, we pop back up. Now fib4 can finally make its second call, over to fib2. But wait a second, notice anything? We're calculating fib2 again. That repetition is a huge clue about what's really going on here. So this recursive solution, it's really elegant, right? It perfectly mirrors the math. But that elegance, and especially that repetition we just spotted, it comes with a hidden price tag. So let's talk about complexity. So get this. To calculate the fourth Fibonacci number, a tiny input, our code actually made 9 separate function calls. Not 4, 9. For such a small number, that is a shocking amount of work happening behind the scenes. And that, right there, is the direct result of that branching tree structure we saw. Because each call can potentially create 2 more calls, the total amount of work doesn't just grow in a straight line. It grows exponentially. The workload just explodes as our input number n gets bigger. Now, in the programming world, we have a fancy way to describe this: big O notation. The time complexity is pretty close to O of 2n. And that 2 in the formula, that is not a coincidence. It's there because our function makes 2 recursive calls. What this all means is that the code is beautiful for learning the concept, but it is terribly, terribly inefficient for actually calculating large Fibonacci numbers.
So this leaves us with this really interesting trade-off. We've got this clean, elegant, easy-to-read code that's also just incredibly slow because it's doing the same work over and over again. So the question is there a way to keep that nice recursive structure, but get rid of all the inefficiency? Can we have the best of both worlds?
And the answer is a big yes. Understanding why it's so inefficient is the key that unlocks the solution. It opens the door to some really powerful optimization techniques, like memoization or dynamic programming. But, well, that's a whole other can of worms, and definitely a story for another explainer. Thanks for joining me.